Okay, welcome back, and yes, good day to everyone. So I am going to continue my discussion tutorial for this immediate settlement. Now it's for the second the method that we are going to use. This is the Schmertmann'S method. This is for granular soils or for cohesionless soil. And take note that this is, if you are using this method, you are going to take into consideration a depth just equal to 2b. All right. So if you're like influence factor that you're going to identify, you're going to plot this one. For example, this is for L over B is equal to 1, then this is could be most likely will be your value of your IZ. Okay, so take note that it would start with 0.1 and then goes to 2B. Alright, so if this is greater than 10, then this could be your chart. Now IZ is the net foundation pressure increase, by which delta P, or the change in the pressure, equal to the effective overburden pressure at a depth of 0.5 B. That means if you have this footing, 0.5 B is over here, 0.5 B. Okay, so we are going to use this formula, by which take note X is 2.5, that is square footing, and 3.5 for a long footing. IZ is the influence factor, which could be identified from the chart that we have, this one, and it's going to be the value for each layer at the center. Okay, at the center of the layer. C1 is the correction factor for depth of the foundation, which you have here the effective pressure and then the net pressure of the soil. C2, when you have to do a correction factor for creep in a particular time in years after the application of the foundation. So T could be like 1, 2, or 3 years, or the number of years. So Schmertmann's method, this strain influence diagram must be redrawn so that we could identify the exact value of your IZ, and then where this effective overburden pressure should be at a depth of 0.5 B, that is from the footing. So here should be 0.5 of B that we are going to compute for this effective pressure. And if it's long foundation, we are going to use 1B. Again, 0.5 it is for square, 1B so if it's for long foundation. So how are we going to calculate, since this one is a square footing, so meaning we are going to use 0.5B. So what is the effective pressure here? Okay, you have like from the ground is like 0.75 here, and then here should also be like 0.5 of B, since B is equal to 1.5 meter, so 0.5 of B is like 0.75 meter. That's why you have here at this particular value, you have the effective overburden pressure is like 20 times 0.75, this one, and another 0.75, that becomes 30 kilopascal. Now the net foundation pressure increase, that includes the pressure on the soil coming from the load of the building, which are 300 kilopascal at this point, which is 0.75 meters from the ground. You have the weight, you're going to deduct the weight of the soil. Okay, the weight of the soil, unit weight, which is 20, we multiply it by this height, which is 0.75. This 0.75 is the location or the depth of the bottom of the foundation. So I'll give you 285. Substituting it here in this formula, okay, you'll have 0.81. Now we're going to redraw. This is 0.1. Take note that this is at the base of the footing, okay, which is at 0.75. Now as we redraw, starting here from 0.1, 0.81 is somewhere here, and then you connect it with 2B. 2B is 3 meters. Okay, 3 meters coming from the from this bottom of the footing. So this is from here going here is 3 meters. The depth of the footing is 0.75. That means this elevation is 3.75 meters from the ground. Okay, so we calculate C by just multiplying 0.4 and then the N values or number of blows. That will give you in terms of megapascal here. Okay, now since we already redraw this one, now let us go to for this table. So these are the layers actually. Okay, 0.5, 0.511. So this corresponds to actually a total of 3 meters, which is 2b, right? B is 1.5, so that is equal to 2b, which is 3 meters. And then we can just decide, okay, here is the bottom of the footing at 0.75, meaning this one is 1 meter. If we are going to divide this in 2 layers, that means this is 0.5 and 0.5. This is 1, which has 1 meter. Okay, the N value of this is 12 for these layers. Okay, and then another one here, 1 meter. The N value here is 16, and then another remaining 1 meter here, 1 meter. Now the N value is 24. Okay, now about the depth below the foundation, the center of layer. What is the depth? So looking at here, if this is the first layer, which is 0.5, so the center here is 0.25. Now the center in the second layer, this is 0.5 and another 0.25 here, so that becomes 0.75 here. Okay, this is 0.5 and 0.5, meaning this is 1. So if this is also 1 meter, the center here will become 1.5 meter, because here is 0.5 plus 1 becomes 1.5. And also here, since coming from here to here is 1 and then 1 here is 2, so meaning this is 2.5. So these are the center of the layer, the depth from this, okay, bottom of the footing here. 0.25 for the first layer, 0.75 for the second, 1.5 for the third, and 2.5 for the fourth layer. Okay, let's go back. So since we have already CR, which is just this value, 400 times N, or 0.4 times N to make it in megapascal, or we just divide this one by 1000. So this is 4.84, 0.86.4, or 9.6. Okay, all right. Using this formula, IZ is this one. That means, for example, here IZ is 0.24, and then what is this? This is the layer, okay, which is for layer 1 is 0.5. Okay, and then X is 2.5 because this is square footing, and then CR is this one, okay, 4.8. That gives you 0.01. The same also with here, and then this layer. But first, let us find how to get the value of IZ for each layer. Okay, as I said earlier, that we have to redraw and find this 0.81. all right, then this is actually 0.1. If our graph is drawn to a scale, we can get exactly these values. Okay, for example, the center of layer here, which is 0.5, it intersects over here, and going here is like, it's between 0.2 and 0.4, lower than center here is like 0.3, so according to her it's 0.84. Looking at here, it might not be 0.84, but if your drawing or figure is drawn to scale, then you can find 0.24. This is also 0.81. Okay, next, and the middle and the third layer. Middle and the third layer, you have here this intersection. So this gives you like 0.54. 0.54 is over here. 0.5 is somewhere here, right? 0.5. Now, the last layer, you have 0.18 at the center of this layer over here. Okay, will give you greater than 0.1. That is 0.18. So once you have these values, IZ Okay, we use this formula I discussed already earlier, then we can get this value. Now actually in the calculation of settlement, this is just these values, okay, for each layer. Now we are going to identify this, substitute I should say here. C1, how are you going to calculate it? How are we going to calculate it? Like here, ano, this one, 1 minus 0.5, this we calculated 15. What's this 15? This one, okay, the founding, the depth. Okay, take note of this one. For C1, this is just the stress of that particular unit weight, 20 times 0.75, it gives you 15. And then 285, which is the deduction. You have like the 300 pressure on the soil coming from your building, and then deduct a particular weight of the soil, then it gives you 285. That means you have 0.97 as your first correction factor. And then for example, you have like time in terms of years, like 2 or 3. For this case, you have like just one. Okay, you have just one here. The value, no, I should say 1 year. The value of C2 when t is equal to 1 is equal to 1. So that means this is for your C1. C2 is actually 1. You cannot write it here, it's fine. Then you have net foundation pressure, which is this, okay, and then multiply it by this total value of each layer. And this one actually is already like the settlement, but we apply some correction factor. That means your total settlement is 24.9 millimeter, or should we say 25 millimeters. Okay, again, this is just the location, the settlement at one location of your footing using Schmertmann'S method, and you have to check with the rest of the footing to identify if there would be like regular or average or the same values of your settlement in all of your footing or foundation, footing structures. So that's all for today. Thank you, and see you in the next video.